Okay, so let's continue. In the previous two examples, we can see that there is a leader and a follower. Okay, the leader moves first, and then the follower moves after the leader. So, before the leader makes her decision, of course, if you are the leader, you're going to anticipate what the follower will do, right? And you will pretend yourself as a follower to think about in each situation what you will do. Okay, what you will do. So in general, this is how we solve a game. When we solve a game, we think we are those players because we can take their perspective to maximize their profits. So if there are multiple stages in a dynamic game, what we should do is to do the analysis from the last stage. We're going to think that at the last stage, how would this player act? Okay, because this player can see the whole history of this dynamic game. And then this player can make her own decision without worrying about the other players because no other player is going to move afterwards. So we can solve the last stage and then we will move back to the second last stage because if we know what will happen in the last stage, we can fully determine what to do in the second last stage. Okay, and then the third last stage, and so on until we can solve the first stage. We will continue this process backwards. So in general, we say we use backward induction to solve a dynamic game. Okay, that's just the general way when we analyze a dynamic game. So let's see another example to give you more ideas. Suppose I have this three-stage dynamic game. Player 1 moves first A or B, and then player 2 C or D, and then the turn will go back to player 1. Player 1 can choose E or F. So in this three-stage game, we want to ask what will be the equilibrium outcome. Okay, so let's think about it. We start with the last stage. So for player 1, he will think, okay, if I choose E, I get 3. If I choose F, I get 2. So I will choose E. So now it's player 2's turn. In stage 2, player 2 will think, if I choose C, I get 1. If I choose D, I'm going to get 0. Okay? If I choose D, I know the result will be here. So I will get 0. So that means if I am player 2, I'd better choose C. So now it's player 1. For player 1, he thinks, okay, if I move to the left, I get 2. If I move to the right, player 2 is going to choose C, so I'm going to get only 1. Okay, 2 is greater than 1. So if I am player 1, I should choose left or A. So that means what will be the equilibrium outcome? The outcome is that player 1 choose A and the game finishes. Okay? There's no chance for player 2 to move because player 1 will finish this game in one shot. However, for this particular game, we can make more discussions. We say that when player 2 has the chance to act, here, player 2 should choose C, right? But is it always the case? Is it really the case? Let's think about it. Suppose player 1 is rational. Then player 2 should never get a chance to act, right? So if you are player 2, you think about this. You think about player 1 and you understand that player 1 should choose A and you don't really get a chance to make a response. So that's a typical situation. But if you are player 2 and you really be called to make a decision, then somehow that tells you that player 1 is not fully rational, right? If player 1 is rational, player 1 does not do that. So that must be player 1 has something that you cannot predict. So if player 2 has the chance to move, he somehow should not believe that player 1 is 100% rational. So if player 2 choose D, again there is some possibility for player 1 to choose F, right? If player 1 is rational, player 1 chooses E. But because player 1 is not fully rational. There are something that we don't understand on player 1. So if I choose D, player 1 probably has some possibilities to choose F, and then as player 2 I will become very rich. So that means player 2 should not completely abandon the choice D if he can get a chance to move. Okay, so let me summarize. As player 2, if I really get a chance to move, I either choose C to win $1 for sure, or I choose D and try to have some possibility, try to really be lucky so that player 1 choose F. So I probably can bet on player 1's bounded rationality for me to get so much money. So we can say that if some of the players are boundedly rational, then to predict the outcome of a game will become much more harder. Boundedly rational or bounded rationality has been studied in all kinds of subjects. People build different kinds of game theoretic models to deal with bounded rationality. For example, when you have multiple choices, you probably do not always choose the one that maximizes your payoff. You probably will do a randomized choice, but it's just that the one that maximizes your profit can get the highest probability. Okay, something like that. So people use different kinds of models to deal with situations in which players are boundedly rational, with some probabilities, or sometimes they make wrong decisions, or they just cannot know everything in a game. Okay, those are some topics in the typical game theory course, but we don't have time to talk about it. So just keep in mind that even though we assume people are fully rational, that's not the whole story about game theory. Actually, people have studied bounded rationality with all these theories and models. Okay, so anyway, yeah, just forget bounded rationality. It's not a topic in this course. So let's move back to our general situation. Let's discuss about leader's advantage. In the game Bach or Stravinsky, being the leader is beneficial, right? But in prisoner's dilemma, being the leader or not does not change anything. So if you are playing prisoner's dilemma, you don't care whether you are the first mover or the last mover. In many chess games, okay, we can say that being the leader is advantageous. So if two players are playing chess, typically the one that has the higher probability to win is going to be the second mover, right? To make the game somehow more fairer. So we probably want to ask this question: is it always good to be a leader in a game? And immediately you can see that's not true in general. For example, if we are playing matching pennies, so matching pennies was the game that if two players choose the same thing, player 1 wins, or if they choose differently, player 2 wins. Okay, if you are playing a dynamic matching penny game, then if you are the first mover, if you are the leader, you always lose because the follower can choose something that is different from you. I mean, if you are player 1. Okay, so try to do a careful analysis about dynamic matching pennies to show that you will always prefer to be a follower in this game. So let's conclude this section with this ultimatum game. This game is something that typically used to show that game theoretic models has its limitations. So let's talk about it. Player 1 is the first mover. He or she decides how to share $1 with player 2. So player 1 is going to choose a share, which is S. S is a number between 0 and 1. And then player 2 will accept or reject an offer. If player 2 accepts, player 2 will get that S dollars. And the player 1 will get the remaining part, 1 minus S. or if player 2 rejects, none of them will get anything. So we can describe this game with the game tree here. It's still a game tree, it's just that for player 1 there are infinitely many actions. So for player 1 you cannot just draw several branches. Now it's the player 1's tree is actually a triangle because there are infinitely many options for player 1. But anyway, you know, the two extreme cases is that S is either 0 or 1. S is a number between 0 and 1. Given any choice of S, player 2 will choose accept or reject. If player 2 rejects, none of them get anything. Or if player 2 accepts, player 1 can get 1 minus S and player 2 can get S. That's the game. So let's think about it. Both of these two players are completely rational and act to maximize their expected payoffs for themselves. What will they do? So again, we need to do backward induction. Player 2, given an offer S, what will player 2 do? Player 2 thinks about it. If S is positive, then S is greater than 0. So in that case, S should be accepted, right? Even if S is just 0.01, it's better than nothing. So player 2 should accept any offer that is greater than S, greater than 0. That's player 2's best strategy, right? And then it comes to player 1. Will player 1 choose say 0.1? No, because player 1 can do better. Player 1 can choose 0.05. Is that the best? No. Player 1 can choose 0.01 and so on and so on. As long as player 1 can cut down the share to player 2, player 1 will do that. Okay? So eventually player 1 will offer nothing. So if we want to describe this game, then we can use a timeline to do it. Player 1 chooses a number between 0 and 1, and player 2 chooses accepts or rejects. Say that player 1 will get $1 and player 2 will get $0 in equilibrium. Or technically, we should say that player 1 earns something that is very close to 1, and the player 2 earns just the remaining part. If player 1 wants to make sure that player 2 will accept, player 1 must leave at least some positive things, or this epsilon, to player 2. Okay? So if player 1 really gives player 2 nothing, then player 2 will, of course, have some probability to reject the contract. Okay? But theoretically, I hope that you can understand that by our definition about equilibrium, only 0 accept and 0 reject may be an equilibrium outcome, because player 1 will never be satisfied with any positive small s. Okay? That's something to keep in mind. But of course, you can say that this is not very realistic, right? Because if you are really playing the role of player 2, it's highly possible that you will be angry about a very small s. You will be angry if player 1 only gives you a little thing. So if you want to become to be more conservative as a player 1, you probably will give player 2 a 0.3 or 0.2.5, something like that, so that you can make sure that you can really earn that money. But this model actually still tells us a lot of things. The thing is that think about wage negotiation between an employer and an employee. If you are an employer and you are going to give your employee a certain money as the salary, what will you do as an employer? You will try your best to make the wage as small as possible, as low as possible, right? If some other guy is paying say $1,000 per hour to hire an employee, then what will you do? you want to make your offer as small as bad as possible, but cannot be worse than $1,000, right? All you need to do is to make sure that player 2 or the employee will accept your offer. So you will keep trying to make the offer worse, and worse until you cannot do that anymore. Okay? And this typically happens in all kinds of companies, right? Many companies, they just do very bad to their workers. They try to cut down their wages as much as possible. And why do they do that? This model provides an explanation because they are somewhat rational. If they do not take player 2 or the worker's utility or payoff into consideration, then naturally people does that. Okay, so this is something that we can tell from the model. So of course that outcome is not very promising. People get very unfair allocation. Everything goes to the first mover, goes to the leader. So probably you want to think about how may we modify this game to achieve a half-half allocation. A half-half means somehow they play this game and eventually they get half-half. Somehow they find a game rule to share this $1 and at the end in an equilibrium they get half-half. Okay, there are all kinds of possibilities. Think about it, design your own rule, and ask yourself what will be the equilibrium outcome. We're going to discuss this in class. Okay, thank you.